Okay, perfect. So welcome everybody to another MCRN Colloquium. Today we have a great speaker today. We've got KK Tung, Kit Tung. Professor Tung is at the University of Washington in the Department of Applied Mathematics. Before that, he's been at some prestigious places, did a postdoc at MIT, got his doctorate at Harvard, and even did a bachelor's and master's at Caltech. So all the big ones. So great resume, and even more so as one of the original founding members of MCRN in the past. So I'm very honored to have you here speaking. We're all very excited, I think, for this talk. And today he'll be talking about the catastrophic collapse of the Atlantic Overturning Circulation, which we know as AMOC. And I guess there's a question if it's near a tipping point. So with that, I'll turn it over to you, and looking forward to it.
Thank you, Christian. Thank you, Emmanuel. I'm happy to see a renewed activity from MCRN. I hope I will be able to contribute a little bit towards the dialogue. So I'm going to talk about AMOC, which is Atlantic Meridional Overturning Circulation for short. And is it false alarm or is it early warning sign? And my collaborator is Xianyao Chen in Ocean University of China. Now, this AMOC spans two hemispheres, from Antarctic to the Arctic. And when it crosses over the tropics, it absorbs heat from the sun, and then it transports such heat northward. And then it gives up heat to the atmosphere, as the atmosphere is much warmer, much colder. And then it sinks, and then the cold water returns beneath 1,000 kilometers. This is a massive current. It's measured to have a flow rate of 17 sverdrup. One sverdrup is 1 million cubic meters per second. And one sverdrup is 5 times the flow rate of the world's largest river, the Amazon. So this is a huge current. And the heat that it transports northward is measured in terms of petawatts, 10 to the 15 watts. So the thought was that since this current is keeping Europe and US warmer than it should be at the same as it deserves to be at that latitude, what if it collapses? If it collapses, then would it bring in an ice age? And indeed, this has been raised as a concern. And the movie The Day After Tomorrow dramatized it, and the figure from the right seemed to show that the ice age came as fast as 3 days. So that's a dramatization, but is there any basis behind it? Well, there are some. In GCM's, general circulation models, we can do experiments where we artificially inject large amount of fresh water in the North Atlantic, and it could actually stop the current. And in paleoclimates, there have been these weird
You're muted, KK.
Oh, I think, sorry.
You couldn't hear me any all
Just
this
dropped
time?
out, now we're back, yep.
Okay. So as the ice age about ends, the large amount of fresh water that floods into the North Atlantic because of melting ice. And it then, because fresh water is less dense, it stopped the sinking. And then when it stops sinking, there's a lack of northward transport of heat, and then the northern hemisphere snap back into ice age. This happens many times. So the question is, what happens under global warming? I want to mention that superimposed on the AMOC is also the Gulf Stream. The AMOC is 17 sphere drop, but Gulf Stream is 30 sphere drops. But Gulf Stream, not all Gulf Stream sinks. It does not really overturn. It just returns at the same level. And the overturning part is the part that is expected to be affected by global warming because the melting ice, fresh water inhibiting the sinking. The Gulf Stream may or may not be affected. And therefore, you see all these debates online where a headline would say, as long as the earth turns and the wind blows, Gulf Stream will never collapse. So it's just playing on the different definitions, what AMOC and Gulf Stream is. That not definitions, but different characterizations of this two current system. Now, currently there have been quite a bit of publicity surrounding the AMOC. I'll read some. The Guardian says that the currents are already at the slowest point in at least 1,600 years, and then they may be nearing a shutdown. BBC would say the Gulf Stream system of warm currents will collapse as early as 2025 next year, a scientific study has warned. CNN would say a crucial system of ocean currents is heading for a collapse that would affect every person on the planet. Be very worried. Gulf Stream collapse could spark global chaos by 2025. Now, these are not just speculations. They were based on some very substantial publications in high-impact journals, such as Nature Climate Change, Nature Communications, Nature Communication, Nature Geophysics, Nature Communications, etc. I listed a few. There are quite a number of other publications. And then there is also the interest on the tipping points, especially in Europe. There's been quite a bit of interest on tipping points. I will define tipping points later, but a simple way to do it is that it's like a chair that you tip a little bit, it comes back. You tip a little bit, it comes back. But if you tip too much, then it will tip over. And the point of no return could be called a tipping point. Central to all these global tipping points is the Atlantic circulation. And it says in slowdown since 1950. This is one of the signs that it is in trouble. There are others like the Greenland ice sheet is losing. And there was a study saying that there is early warning signs of tipping in the Greenland ice sheet. There are controversial debates about whether or not Amazon rainforest would vanish. The coral reef is unrelated to all these. And then this Antarctic ice sheet in the west may be near a tipping point. So let me introduce the concept, the tipping points. I teach a course for sophomores and juniors on mathematical modeling. We actually use simple examples to teach them the mathematical concepts. So here, if I use an example of fisheries. Okay, suppose n denotes the population of the fish, and the H is the harvesting rate, and in the absence of harvesting, we have a natural growth rate of the fish, and for sardines, it grows like this. The reason I use sardines is that before 1920, there's a flourishing fishery industry in the Bay of San Francisco. It disappeared now. You no longer get sardine from San Francisco. You get it from Norway. So the mathematics is that if I plot out what this F look like, supposed to look like this, then at where it hits 0, it's where d dt of n is 0. So we call it an equilibrium point or fixed point. The fixed point could be stable, it could be unstable, but we actually know which direction it's going depending on the sign of this F. So if F is positive, I draw an arrow towards the right, meaning that the fish population will grow. When n is negative, as in these two places, I draw an arrow to the left, and the population will decrease. At this point, which is the so-called carrying capacity, it is a stable equilibrium because you perturb to the left, to the right, it all come back to that point. It's a stable. But there is another point here where you perturb, it goes away. And one way it will go is towards extinction. Okay, now we add harvesting. Harvesting is proportional to the effort, which is E, and it's also proportional to the amount of fish that's available at a certain time. And Q is just proportionality constant. So we plot this as a straight line, and the slope depends on E. Okay, so when we cut it like this, it changes the location of the equilibrium points, but this one is still stable, and that one is unstable. And at this point, if you harvest at this point, it's called sustainable harvesting. Now, if you get greedy and start to harvest too much, at a certain point, this two equilibrium, one unstable, one stable, will merge towards each other at this point. It merges. And beyond that, the arrow just goes in one direction towards extinction. So you harvest too much at this point, you will lead to the fishery going extinct. And one point I want to note for later purposes is that as you approach this point, we could call that a tipping point, the rate of change, which is the difference between these two curves, is very small. And that 0 there is quadratic, double zero, while these other zeros are linear, simple zeros. The simple zero fixed points in higher dimensions, in dynamic systems, this will be called saddle node bifurcation. But in one-dimensional system, you don't need to go that sophisticated. Okay, let me give another example. This is Stommels model. I'm not going to use Stommels simple model for the rest of the talk, but I want to use this to introduce the concept of tipping points. Now, in the Atlantic, the most saline part of the water is in the subtropics. And it's bisected by the fresh water coming out from the Amazons. And so saline water is dense, but as it's transported northward, it loses heat this warm and saline water, the salt remains, but the heat is lost. It gets cold, and cold water is denser, and so it sinks. And then it goes around in the overturning circulation. So Stommels model is thermohaline circulation, considering both temperature and salinity. Let me talk a little bit about salinity by showing this figure. Let me see.
Earth's climate and the circulation of deep ocean currents are strongly influenced by the saltiness of the sea surface. So why don't we have detailed maps that show its rapid changes? Well, now we do. After more than a year of continuous measurements, NASA's Aquarius instrument aboard the Aquarius SAC-D spacecraft has given us this new space-based view of sea surface salinity. A closer look at the data reveals some fascinating features. Our focus first turns to a salty patch of water in the North Atlantic Ocean. Evaporation of water from the sea surface leaves behind large amounts of salt that contribute to the active zone of high salinity water seen here. Conditions are different in the North Pacific Ocean. Near the equator, in one of the wettest regions on the planet, heavy rainfall adds an abundance of water to the sea surface. This results in the dark blue band of low salinity water off the coast of South America and Central America. Rivers can also influence the amount of salt on the sea surface. Every second, millions of gallons of fresh water flows from the Amazon River into the Atlantic Ocean. The effect of this is a sinuous plume of low salinity water that extends from the mouth of this great river. At high latitudes, the seasonal melting of sea ice causes a sharp decrease in sea surface salinity. We see examples of this in the Labrador Sea and the coastal waters that surround Greenland. In spring and summer, surface currents transport the low salinity water south, where it meets warmer and saltier water carried north by the Gulf Stream. The contrasting patches of high salinity water to the west and low salinity water to the east of the Indian subcontinent are due to a combination of geography and climate. To the west, an arid climate and lack of fresh water input yields the salty waters of the Arabian Sea. To the east, monsoon rains and freshwater outflow from the Ganges River keep the Bay of Bengal far less salty. Without satellite observations, these global changes would be largely invisible to us. Ongoing measurements by Aquarius will help scientists better understand our vast oceans and how changes to ocean circulation and the transport of water through the atmosphere may impact Earth's climate.
Okay, so Stommels model consider both salinity and temperature. So consider two boxes, one tropical box, this is only the northern hemisphere, and one high latitude box, only the northern hemisphere. And the salinity is measured by S, temperature is T. In the tropics, you have input of solar energy that warms the waters, and you have an evaporation of fresh water that increases the salinity. At high latitudes, you lose heat to the atmosphere, but precipitation also and ice melt from glaciers also adds fresh water, decreasing the salinity. And the thermohaline circulation has the circulation which depends on the density differences, high latitude versus low latitude. But density depends positively on salinity, but negatively on temperature. So the competition of these two effects is what is in Stommels' model. As I mentioned in the last view graph, at high latitudes, temperature changes if warm waters are vectored into it, but it loses energy to the atmosphere if it's warmer than the atmosphere. And in its salinity, also, salinity is transported from low latitude to the high latitudes, but precipitation lowers its salinity. It's the opposite in the tropical box. So these are the four equations. And the thing we do when we teach our students, what we do first with this dynamical system is to find the equilibrium. So you find the equilibrium. There are four equilibrium because Q is absolute value of the psi, but psi has two signs. So we could either say psi is positive, then the same as Q. If psi is negative, then you have the other two solutions. One of the solutions is inconsistent with that assumption, that is, you assume it's negative, but it shows up to be positive, so we eliminate that. So the three, so 1, 2, 3, and it depends on one parameter, which is the control, F. F is non-dimensionalized form of precipitation or freshwater input. So there are three solutions. One is stable. That is, you can do a small perturbation of the equilibrium and finding that the solution the perturbation exponentially decays and back to the original solution. So it's stable. The dashed line is an unstable solution. This is the second solution, and that is stable. So suppose currently we are here and we perturb it, it would still come back here. But at a certain point, this is the so-called tipping point. More precisely, mathematically, it should be called saddle node bifurcation. It's when an unstable fixed point merges with a fixed point. Here, a quadratic zero. At this point, if a perturbation exceeds that, that is, you put too much fresh water in there, it goes over here, then has no place to go but to the lower stable equilibrium. Then you say, that's too bad. Let me try to save the situation by reduce the freshwater input. So I reduce the freshwater input, but then it cannot go back there because it's being repelled by the unstable equilibrium. And the only way it will go back there is to go all the way to here and then back up there. So this is a nonlinear phenomena called hysteresis. And the concern was that once we push AMOC beyond the tipping point, it will become irreversible. Now, if we are here and we say, are we close to the tipping point? Well, there is no warning. There's no early warning signs, okay? In a deterministic system, there's no early warning signs. But when you add a little bit of noise, the situation changes. So let me play a video of someone, Tim Lenton, who had a really good animation of the tipping points. Let me see how come it doesn't show.
Have the video on your laptop. You could stop sharing this and show your video.
Where?
If you have the video saved on your laptop, you could
Yes.
stop sharing this and then.
Yeah, let me escape and go here. Yes, you're right. Well, it does not. Oh,
Thanks very
it's on.
much. Yeah, I'll try to
It's mentioned.
introduce those climate tipping points, and then I want to
You may need
talk
to reshare your screen.
a little
Though,
bit
we're not
about
seeing the video.
how there are general early warning signals of tipping points in
You might
complex,
want to reshare your screen.
and we can
Yeah,
see those early
right.
warning signals before tipping points in the climate system. And maybe you've heard a tiny bit about that topic from other speakers. We'll see. Okay, let me
Can you
just
see it now?
share the screen and we can get started.
Yes, we can. Thank you.
Can you see it now?
So
Yes.
Yes, we can. Yes.
Going to go backwards. But so yes, climate tipping points. But to start with, I'm going to just show this movie of a system with two alternative stable states, the two valleys, and I'm forcing this system towards a tipping point. I'm forcing it fairly slowly, and it's also subjected to some variability, some noise that's pushing the ball around. But as we can see, the state the system started in is losing stability. And at some point, a small nudge there is going to be enough to tip the system from one state or attractor into another. Before that tipping point, if you're watching closely, you can see some general behavior. The ball is going to roll around slower in the valley as it gets shallower before you hit the tipping point. And that really is the general early warning signal that I'm going to come back to later. The general early warning signal that a tipping point is approaching. Now, I'm just going to let it.
Okay, so let me summarize. You have this valley that he showed. Too bad that is flipped around, left to right. So if you're far from the bifurcation and you have some noise will be damped really fast. As you increase the freshwater input, this valley gets shallower as it loses stability. And then your oscillation will get larger and larger. And after a point that when you still increase the freshwater input, it flips over to the other state. Now, to understand this, you can linearize your state around that fixed point. And as lambda, if the system is stable, lambda will be negative. But as lambda increases from negative value towards 0 in a tipping point, then things happen. The noise will increase in variance because it's less damped. And then also, it retains more of the memory, and therefore, its autocorrelation increases. So increase in AC1 and variance are two classic early warning signals of a tipping point. Dillipson in 23 did a more mathematical work in, I think it's in Nature Communications. And this publicity about AMOC collapsing next year is from them. Susan Dillipson is a statistics professor, is Peter Dillison's sister, and this is an ideal collaboration. They first show that near a tipping point, saddle node bifurcation, there is universal effective dynamics, and the dynamics is described by a stochastic differential equation, because you need early warning signs, so you need to add noise as a quadratic zero. And For those of you who are not familiar with this notation, if you divide it by dt, then it looks like a differential equation. The reason you don't divide by dt is that sometimes these things are not differentiable. Okay, xt is the AMOC index, and mu t is your control, like freshwater input negative of that. So let's the problem is that Didlefson and Didlefson cannot solve this equation. So they expand this equation around one of the fixed points, and they come back with a first order 0, and with a parameter that depends on the control. Okay, this assumption was criticized by several scientists in the literature, and the problem is that this universal behavior is only valid when you're very, very close to a tipping point, to southern lobe bifurcation. Otherwise, as we know in Taylor series expansion, any linear terms would dominate over quadratic terms. However, after they got the quadratic term, then they expand it and get a linear term. So that's some inconsistency. A second concern was that this is non-autonomous system. I think 2 weeks ago, we have a speaker about non-autonomous system. And Didlefson treated it as if it's an autonomous system under the assumption that the freshwater input is so slow that at every point that they are considering, it could be considered as a constant. That seemed to be okay, except near a tipping point when the coefficient goes to 0. And that's when you have d mu dt over mu going to infinity, and you cannot make that approximation. Okay, so the first problem was that they simplified it too much. We could actually solve this equation. For those of you interested in mathematics, this would be the direction to go. A colleague of mine, Professor Hong Chang, actually published a paper in Physica D with the solution to this equation, also for the non-autonomous system. Now, the difference between these two systems are that at the tipping point predicted by this, it's not irreversible. There is still a window during which if you reduce freshwater input, it could save the system. You'll return to a stable situation. And then, but if you keep continuing putting freshwater input, at a certain point, you would get a irreversible point of no return. That's the classic definition of tipping point. But that point could be considerably delayed. So there seem to be two approaches here. One is mathematical. You pursue this, get the formula for the delay, and putting in the rate of freshwater input, and putting in all the parameters that is relevant for the AMOC, and then find out when that point of no return is. If it's beyond 2100, then that's consistent with what most IPCC models would say, that it's not likely to have a tipping point before the 2100. And so that's one approach. The other approach, which I would take in this talk, is more physical. It seemed to me that mathematics, this approximation, is the least of their troubles. Now, so let me continue. Didlefson tried to solve this, and the solution is readily available in Ornstein-Uhlenbeck process. In this process, the solution says the autocorrelation is exponentially decaying with alpha delta t. Delta t you take as 1 month. So alpha will be log of rho. So when rho reaches 1, your alpha is 0, and that's their definition of a tipping point. Also, the variance is gamma squared. These are the noise. Variance of noise is the noise level, sigma squared, divided by 2 alpha. So when alpha goes 0, variance goes to infinity. Now, this OH process was used quite a bit as model for stock prices. Another colleague of mine, Tim Leung, who directs our computational finance program, wrote a book on mean reversing stock market. That is, stock market has been observed to be mean reverting. That is, they are actually tested with the historical prices. If you sell when it's high and buy when it's low, would you make money? You have the automatic execution. Would it make money? And the book says, yes, it would. It would. So why doesn't everybody do that? That is, there is this problem of financial crisis. When financial crisis comes, it drops so much and it does not necessarily return. And the financial crisis is analogous to our tipping point. And this OH process is not applicable near a crisis, okay? You could see the volatility of stock market as measured by VIX index spiking up, but sometimes spikes without going into a collapse. Sometimes it spikes, it would go into a collapse, you just don't know. Okay, so you don't make money using this. You make a little bit of money and then you lose it all in a financial crisis. Now, the problem with this type of research is that we don't have a long enough record of AMOC. There's a rapid system of measurement off the coast of Florida that measures the flow rate of this AMOC, and it only has 20 years of history. We need at least 120, 150 years because AMOC itself varies on a 65-year cycle naturally. So if you want to see what's happening, you need to at least more than one cycle. There are two types of AMOC proxies that are being used. One is SST-based, and one is salinity-based. The SST-based is quite popular with the Europeans, the Ramstad et al. They propose that you see that there is a patch of cool water in the North Atlantic. It's called warming hole. It's not warm as much as the surrounding. If you take the temperature there, it's subtracted by the Northern Hemisphere mean, or you subtract it by the global mean, SST, you get an index, which they claim measures the AMOC, because they think that this is cold because AMOC has been slowing. Okay, so this is Dillison and Dillison. So the variance goes to infinity, and you know that it's unrealistic for this calculation that will go to infinity. All the correlation goes to 1, and this is just the noise. This is their freshwater input. You see here that they use 2 times the global mean SST instead of just 1 time as what Ramstad et al. Uses. That's because if you use 1 time, there's no decline in this AMOC index. So they make it 2 times and they curve it down so that they all collapse at the same time. So it's number 1. Number 2, their solution is not valid here. Okay, another try, I think it's kind of admirable. It's by Nicholas Boas in 2021. This precedes the Dillison and Dillison's work. And this is more empirical. It does not require OU process. It says, as I mentioned before, near equilibrium, you can expand it linearly, and you perturb this point by some noise. And they are using the AMOC proxy index, and And they use regression analysis to find lambda. If lambda is negative, then it's stable. If lambda is positive and stable, lambda is 0. It's approaching 0 from below, you're approaching a tipping point. And the fact that the lambda is approaching from below 0 is an early warning signal. So they tested this with an example. If you have a cubic nonlinearity where it does have a tipping point, southern node bifurcation, his method worked. And the noise, when you blow it up, see that the variance is increasing, the AC1 is increasing, lambda is increasing from negative to positive. When you have a model without any tipping point, if you add a noise that is increasing in time, you could still get false alarms because you got a variance that's increasing, AC1 is increasing, and then you got lambdas increasing from below. He came up with generalized least square that overcomes this problem. So the red line is when you use generalized least square, then you don't get this feature. So he's applying this to his data. So this is his procedure, and they use our salinity proxy. It's from 2018 Nature paper. He extended our proxy to 1900 because he need at least 120 years of data. And this is what he got. So the left-hand side is the SST-based proxy. I'm not going to talk about that. I'm going to talk about the right-hand side. And you see that 2 of the index is from North Atlantic subpolar latitude. It's from our index. The pure green one is decreasing, and the black one is decreasing. Okay. Turns out they had a sign mistake. If you change the sign back, then it would be increasing. But there is one that decreases even more. That is the South Atlantic salinity. Let me talk about that in a minute. But you can see that their lambda is increasing from below. It will hit 0 in 2000. So meaning that we are already in a tipping point. The variance is increasing. The autocorrelation is increasing. So here, Boas said, this is scary. Now, our salinity index says, we published this in 2014. As AMOC increases, it brings more salt and warm water northwards. So when you get more salt, it indicates that you have an increasing AMOC. When you have less salt, you have a decreasing AMOC. So that's fine. But another region is the South Atlantic. This is a region from which salt is taken away. So when AMOC increases, the salinity should decrease. When AMOC decreases, salinity should pile up. So this is what they found, that in this paper, they found there is a likely accelerated weakening of Atlantic overturning circulation because there is a salinity piled up in the South Atlantic. So you take the South Atlantic salinity and you multiply by -2, that is Boas index. And from there, he concludes that the AMOC is slowing. However, should you trust this? You looked at the measurements of salinity. And there was there were almost no measurements before 1950. Occasionally, you have a research ship that was out there, and it rained for a month, and they measured some negative salinity. And then, as time goes on, we have a few global campaigns, and then now we have Argo floats that we are measuring more and more salinity. But that corresponds to the coverage. That is, if you take for the red line, the percentage of data points that has actual measurements, you see that this variance, which is the blue line, is associated with increasing coverage. And the black line is the variance, and the blue line is the lambda that goes from here to 0. And similarly for the northern hemisphere, even though there's a little bit more measurement, these features of increasing variance, black line, and positive slope of lambda are correlated with the increasing coverage. So we are seeing a lot of these kind of phenomena, these early warning signs called EWS, touting as really pointing to the collapse, but a lot of them are due to data. There was no data, and then now you have data. Therefore, you have an increase in variance. Now, to show causality, we take a few models that do not have early warning signs. That is, the AMOC is stable. And that's the blue line from CCSM4 and GFTL. And the blue line saying that there is lambda is flat in the northern hemisphere, subpolar region, and in the southern hemisphere. But now we subsampled it with the actual historical data coverage, and then you get the red line, and then you redo the calculation again, you get this early warning signs. So you get early warning signs, but it's due to the data coverage. This proves that. So I'm getting towards the end of my allotted time. So let me mention whether the AMOC is slowing. There have been quite a bit of publicity about AMOC is weakest in 1600 years. And there's the high impact journal saying exceptional 20th century slowdown by Ramstock and Mann. But the problem with that is that this warming hole is not necessarily related to AMOC. And there's a paper by her et al. This Mark Kane and Amy Clemens student that has an atmospheric model with a slab ocean, no circulation, and they generated this. And it generated this proxy similar to what Ramstock had used. So this is proxy that they use to say that we have a AMOC decline is not physical based. Now, in our 2018 paper in Nature, we actually find out using a number of proxies what AMOC is doing. It's going up and down, 3 sphere drops, up, 3 sphere drops down in a cycle. We think it's natural. And the SST-based proxy is what Ramstock used. They're using the peak here and here. So they claim 15% decline from mid-20th century to recent. That is this decline. But they shouldn't be doing that. They should be saying, this is natural, this is natural, this is natural. So looking at more detail, if you take the warming hole temperature, it looks like this is no trend. Global warming SST, there's a positive trend. You subtract, then a slightly negative trend. It's like this, okay? And, but if I measure it from here to there, I got 3 sphere drops, drop 15%, but you shouldn't be doing that. The last part I won't go into because I'm short of time. The question is, will global warming lead to an ice age? And we talked about this in our 2018 paper, and it led to quite a bit of controversy back and forth, because the paradigm of AMOC is that it transports warm water northward, but it slows down, then it cools. But we actually says that it actually leads to increased rate of warming. So this is what we observe from data. During this period, AMOC is slow. That this is AMOC is slow. The temperature, the global mean SST, the global mean SSTs, the rate of increase is positive. That is a 90%, 90 degrees sort of out of phase. So it's increasing. And we also did a numerical solution. And here is an analytic solution that says that if you have a slowing AMOC, you have an increasing global mean temperature. So conclusion, there's no evidence yet of early warning signals of a pending tipping point for AMOC and no detectable decline of AMOC. It doesn't mean that AMOC is not declining. In models, we can show that there is some declining, but so far it has not risen above the noise. And the work is in collaboration with Shenyao Chen, and we list our publication. The blue ones are the ones that that I've used today. Okay, thank you.
Okay, great. Yeah, thank you for a very, very interesting talk. I guess, yeah, go give some hands, and then if anybody has any questions for KK, please feel free to ask. We have some time. Oh, Hans, I think you're muted if you had a question.
Yes. No, I'm unmuted. Okay. So my question is really sort of more philosophical, in the sense that we are looking at climate system, which, as we all know, is a complex system, and we are isolating one event or one phenomenon, AMOC, and trying to sort of get out of the data that yes, it is declining, or no, it's not declining. Wouldn't it be the case that if something like that were to happen, that the climate system would adjust and we would never see a tipping point?
Yeah, that is a good point. And in fact, I think Carl Wunsch has this idea, and that we all know the Earth has a lot of feedback systems. So if AMOC slows down and transport less heat, there's a certain amount of heat that the Earth, the climate must transport. Okay, so I have a PhD student who wrote a thesis on this. And Isaac Howard has some paper on this, that it would have to transport. So if the ocean is not doing it, the atmosphere will increase its heat transport to achieve that same state. So it wouldn't cool. It would still maintain the same temperate climate. You also imply that maybe it just wouldn't slow at all because there are other feedback process. And I don't think anybody has ever looked into that.
Mm-hmm. So my conclusion is that we are chasing a phantom. Is that realistic, or am I wrong?
What is worth discussing, that is, if these research dimensions turn out to be true, then it would question whether the IPCC climate models are too stable. In fact, there raises possibility that you are not seeing it in IPCC models because these models, the freshwater flux, are too stable. Mm-hmm. And so if you want to predict what's going to happen to our future climate under global warming, you need to fix these models. But I think there's no need at the moment to worry about it, because I don't think you can do this kind of research and test whether or not AMOC is going to tip unless you have 120 years of data, and we just don't have 120 years of data.
Yeah, so our lifetime is too short.
Yes,
That's the problem.
right.
But if you think of the general public that gets these announcements that in 2025 AMOC will shut down, that's very bad publicity, and it affects the attitude of the public towards science. So I think we have to be very careful with making this sort of statements.
Yes, the media is abetting this behavior. There's so many, all major news media publish the prediction that AMOC is collapsing. When we wrote a paper and say it's not collapsing, none of them publish it.
Well, I shouldn't blame the press. It is really up to us to explain what we find, and with all the caveats that are needed.
You're right.
So, to blame the press should not be our attitude.
They are
It's
interested.
yeah, of course, the press is interested in sensation.
Yeah.
But it's us who provide the data, and they interpret it in a very excited way.
Mm-hmm.
So we have to be very careful how we phrase our studies and the results of our studies. So as I said, it's more a philosophical debate.
Mm-hmm.
Hi, KK.
Yes, Gary.
It's nice to meet you. I just wanted to say a couple of things. One, I've been teaching out of your textbook here at Holy Cross. I do a math modeling course, and I've been using your book now, I don't know, maybe 3 or 4 times. And actually, at the end of the course, one of the things I've done a couple times is actually show the movie The Day After Tomorrow. And then we have a fun time, you know, kind of picking apart what was, you know, what might have been accurate and you know, what's ridiculous. Of course, the time frame is ridiculous. But some of the climate ideas in the movie aren't totally, you know, off base. So it's kind of a fun exercise. But I just want to say thank you, you know, thank you for the book, and I've really enjoyed using it. I seem to recall in the movie that it wasn't just about the AMOC slowing down, but doesn't it like change direction? Isn't that kind of the theme, you know, with the scientist there? And so that, you know, you get this massive cold freeze because it just transports all the heat south or something. But that's not what people are warning about. Am I right about that? If I'm understanding what you're saying, that the issue with AMOC is the slowdown. It's not a change in direction. Is that right?
So this current goes around in about 2,000 years. So for it to change direction in 3 days, just unimaginable.
Right. But so when they say tipping point, that's not what they're talking about. They're just talking about a slowdown that therefore has a big catastrophe with the climate, right?
They are talking about the reversal. If you see my bifurcation diagram, and you see that the lower branch is actually reverse circulation. You see it?
Yeah.
Size negative.
Okay. So they are talking about a changing direction.
Yes.
Okay. So the movie was actually correct. It's just the time scale was ridiculous.
Well, they are using a very simple caricature from Stommel of what's happening. Then we have an expert here, Hank Dijkstra. He has GCM results, and he can fill in what the more realistic models are telling us.
Great, thank you.
I didn't have this Stammel's model in my book, but Hans Kapper has it in his book. You may want to use that one.
Thank you. So KK, if I may ask one other question, this was more practical. Somewhere in the beginning of your talk, you said that the Gulf Stream was not part of AMOC.
Mhm.
How do you mean? I mean, is it
Yeah,
is it
I think
totally
most
different?
people would think that it is AMOC, but AMOC by definition is overturning. And a large part of Gulf Stream is wind-driven. It just goes around the same layer, it returns. And so strictly speaking, it's not AMOC, but part of it does sink, and so it contributes to AMOC, but most of it is just wind-driven in a gyre.
I see. Okay. Thank you.
But this word AMOC, I think the newspaper will have problem using. So they will always say a Gulf Stream system of currents.
Yes.
Okay. Any other questions? Okay, I had one quick one. In the video that you showed from NASA, it seemed, I might have heard wrong, but they mentioned that there was freshwater input from melting sea ice. Which must be from the snow on top, or?
Yeah, so glacier that we know is freshwater coming down. Sea ice, when ice form over sea, it expels salt. And so the salt already got expelled. And then when that ice melts, it restored back to what the original salty seawater was.
Oh, I see. Right, the brine layer that's at the bottom.
Yeah.
Okay, so it's a little bit, yeah, it is a little bit fresher. I've melted it before and measured it in the lab. So you're right. Yeah, that makes more sense.
Yeah.
I just wanted, yeah, I was thinking maybe mostly the snow or something, but that's sort of, it's interesting because then that's an input feature for fresh water. But if you lose enough Arctic sea ice, that mechanism may change things as well. I don't know how that would affect it.
I think the larger contribution are melting from Greenland ice glacier, and then from the Arctic, which collects the fresh water from rivers, and then that when that floods into the Atlantic Ocean, it tends to reduce sinking.
Okay, thank you. Any other? Okay, well, let's thank KK again, and thank you. That was a very interesting talk, and certainly appreciate it. We'll of course post this to YouTube, and hopefully see y'all next week.
Well, thank you all for attending. Thank you, Christian, for arranging it.
Yeah, of course. Yeah, thank you for coming.
Yes.
Thank you, KK.
Thank you, Hans.
Thanks so much for coming.
Yes.
Everyone.